define what artificial intelligence is, at least for the sake of this presentation, um, because we need to have a baseline to start from. And different people, different places have different definitions of artificial intelligence. Think about back when big data, big data is still a thing, but when big data started becoming a term, what is big data? It's kind of the same thing. So I want something that we could kind of base off of for the sake of this presentation. And you might disagree with me on what I define as artificial intelligence, and that's perfectly fine. But kind of this is the benchmark I'm going to use here. And then a few other related subsets of areas of artificial intelligence. Also, some stuff to do with the hype cycles of artificial intelligence, and I'll get more into that when we get into it. A bit of background on generative AI, so everybody knows what that is once we get down to connecting large language models to the systems. And of course, scalability requirements and the actual applications, which I hope everybody's kind of more prepared for that, and some of the technical details I get into on that from the precursory material. So, what is artificial intelligence? And I like to go off of things that start to pass the Turing test, which is the ability to convince a human that the machine is actually a human greater than 30% of the time. Which, if you think of chat bots on the internet and things like that today, we have a lot of things that do start to pass what is artificial intelligence. That said, I also fully acknowledge that what people think of as artificial intelligence today colloquially tends to refer specifically to large language model-based systems. But other systems that aren't necessarily a large language model could also have similar effects. Machine learning being a subset of artificial intelligence where explicitly you are using data somewhere to fit data to it. And this is important because if you think of the last wave of artificial intelligence back in the 90s, there was a lot of expert systems, there was a lot of rule-based, heuristic type systems that could still potentially convince a human that it is a human. But there were gaps in that, and you would end up in places where you would kind of go down the logic, and there were issues with that were kind of based on not having the same compute power we have today to really integrate machine learning into artificial intelligence. Then a subset of this being deep learning, where you're kind of explicitly starting to use black box models, more specifically artificial neural net models, which is what is typically defined as deep learning. There's other versions of this out there that I know other people talk about that have a kind of even more circles inside or outside of this or adjacent, but this is something simple I find is helpful to guide the discussion. So I'm going to show two hype cycles because we're kind of on the cusp of when the newer one was released for 2025. And this is to kind of show how quick this industry is moving, not just in HVAC and buildings, but in the whole world. So you look at some specific technologies here, and you feel free to read up about this more. But the hype cycle is something that gets published every year, and it kind of maps to a conceptual hype cycle, but they focus on publishing it for artificial intelligence at this reference here. But you look at technologies that we're talking about in 2024. Knowledge graphs is important to think about because I'm going to talk about that a bit today and the applications to our industry. Computer vision is something important to think about as well. Think about occupant counting cameras, occupant tracking cameras, all the different security technologies we have. If you go into an airport in North America, all they need to do is have your passport and see your face, and now they know where you are, right? And this is computer vision technology that's got a bunch of deep learning models inside it, and it's pretty successful already in what's considered on the plateau of productivity. Where things get exciting is when you get into inflated expectations, trough of disillusionment, and you see that generative AI is kind of here and about to start going down into the trough. The next graph I'll show you shows that it is there now, according to this particular sentiment analysis system that they use. But you also have a bunch of other technologies like artificial general intelligence, which this gets a bit more nebulous, and this is, experts tend to consider this more than 10 years out. It's very debatable even what, necessarily is artificial general intelligence, right? But this is a reasonable reference point for looking at kind of what's in vogue, what's not in vogue. What are people saying? Oh, this is overblown right now. Now moving to 2025, generative AI is kind of here, but not even on the last graph is AI agents. And I think probably a lot of people on this call will have heard of AI agents by now. But if you look even a year ago, AI agents weren't really a thing. We were just starting to get into retrieval augmented generation, also known as RAG, which I'll very briefly touch upon in this presentation. But there's a ton of content out there on how that starts to fit into agentic AI. But now you can basically build wrappers around generative AI tools, which just the base models, foundation models are kind of going into this disillusionment as well. Partially because I think we're hitting a plateau on performance, but agents allow you to integrate a lot of different systems and essentially use a large language model as an interpreter for human language input to do a bunch of different things. And I'll get into this later in my presentation and some applications of doing that in a building automation system. So to do a bit of background here, I think it's good for everybody to have an idea of what a transformer is and some of the technology that goes with it. So internally, it's composed of deep learning models, but the big innovation on top of it came in a landmark paper in 2017 published by a large search-based company that I don't know if I'm allowed to say the name of because of commercialism policies. But it's a well-known paper. It had a fun title, Attention is All You Need. And ultimately, they were able to build a system that could go on top of artificial neural net models and handle large sequences. So if you think back to translation engines before 2017 and after 2017, this was kind of a jump in the effectiveness of the tooling because the technology in the back end changed a lot. So now you're going from long-term, short-term memory, neural net-based systems to these transformer systems that have this attention mechanism on top. You can kind of see graphically what's happening here is predicting what it is. And in this case, it is probably the animal. Looking at kind of what a transformer does with the input, the encoder, and the decoder, and the stuff coming out. And then vector databases attached to things that start to take information that goes into a system, serialize it in a very highly dimensional format, and this is a 3D concept of a vector database, start to cluster things that are similar based on some numerical values that go in. So a lot of new technologies come out that starts to enable new things, and you start to get fairly large models where this is a visualization of a simplified version of probably the simplest general purpose transformer, which is as the name would imply, general purpose, but it's also a transformer, and kind of the different layers that go through it. So looking at the sheer scale of these things, each of these blocks, I think, is 1,000 parameters in here, and you can sort of see the sheer number of parameters and the different layers and the different machine learning parameters that kind of exist as data is transferred through the system. And if you remember GPT kind of, circa 2018, GPT-2 was kind of the most current model back then, and that had 124 million parameters. This is just 86,000. Nano GPT can do some things, but not even as much as GPT-2, where you could still notice that these were robots on the internet. 3 is where it starts to change a lot, and 4 is where it really starts to blow up, and that's 1.8 trillion parameters. I haven't updated this for GPT-5 yet, but I don't think the jump between GPT-4 and GPT-5 5 is as much as 3 and 4 in terms of parameters. I think it's more a factor of 5 or 10 rather than 100. So with large language models, there's lots of different stuff you can do. When you're referring to the large language model itself, you're referring to a foundation model. Prompt engineering is where you engineer what you put into the model to try and access different parts of the model and manipulate what comes out of it. Fine tuning is where you put in more data with the base LLM and tune it for specific tasks. But be cautious with this because sometimes this breaks other parts of it when you're fine tuning it. So I always try to avoid fine tuning. And then you get into agents, which is this kind of new tech I talked about from the hype cycle, where now you have what's called tools, which is essentially functions, memory, which you would consider kind of your knowledge base that's got documentation that should regularly be accessed to augment the knowledge of the large language model. And then other things it could do with respect to planning and sequencing. And this is where you get into multi-agent architectures and kind of agents that are focused on certain tasks. Kind of the base structure of what you're dealing with an agent is you have an application on top, you have an agent underneath, you have the foundation model, then you have a bunch of APIs that go into knowledge bases functions. And this is kind of the basis for everything that exists in this agentic AI space, which is what I leverage later in some of the stuff we do with large language models in control systems. Of course, there's tangential industries that bring in other useful stuff with respect to kind of the inspiration of things we do in buildings and controls within buildings with large language models. And think about going back to like how ABS inspired insulin pumps. So you could take technology that exists in one industry, move it into others. Healthcare already has a lot of AI-enabled diagnostics. Finance has a lot of fraud detection, which you get into like cyber, similar concepts. Education has personalized learning, which this can really be applied everywhere. And then, of course, content creation, which I use for this PowerPoint to make all these different figures that kind of align with these different concepts. So how do we start to scale algorithms in buildings? I think this is what people came here for, and they're really kind of excited about, and taking these applications and making them real and actually having impact on the industry. My number one thing is we need to remove the PhD from the loop, right? A lot of times these large language models, you have to have a very large amount of training and education to actually work with these in these systems. It's very specialized, and even taking existing software developers, I find, is a pretty big jump. To kind of take someone from your basic regular software development environment and now getting into stochastic systems in the programming, right? So we need to be able to make it so that your standard practitioner can actually implement these systems, which means they either need to be packaged or abstracted into a format where they can be easily deployed. And I have kind of sub rules to this. The machines need to be able to identify the systems, which gets me into some of the prerequisites. The machines need to be able to tune the system models. And I'm very careful about how I said this because I don't think the machines right now that we have currently should directly tune the systems. So you can start to update models. You can start to update your understanding of the real world through a digital twin type process. But ultimately, it knows what the system is and it has a model, and then the human is in the loop to decide how this is deployed, whether through an automated policy or direct intervention. The optimization constraints and parameters really need to be presented in an operator intuitive fashion. They need to be able to see, and this isn't just operators, anyone that interfaces with these systems needs to be able to see and understand it. They don't need to understand all the stuff I already showed with, the parameters and agents and all of this. They need to be able to understand the system that's presented to them and be able to trust the system that's presented to them. Implementation probably needs to start with simple problems, and this is why, as you'll see later in my presentation, I've really focused on zone level control first rather than plants, which is kind of the opposite of a lot of different techniques I see out there. And I fully agree that dealing with larger systems like plants or even air handling units is very important and will yield greater total energy savings and operational savings at the end of everything. But ultimately, the loads of those higher level systems are going to be driven by what's happening at the zone. So I've chosen to look at the zone first because it's a fairly simple problem, and it's a problem that can be duplicated a lot and take advantage of some of the technology that we're starting to see emerge as a prerequisite. Also, compatibility with other supervisory control systems, and this is very control specific, and I'm referencing ASHRAE Guideline 36 here, but really anything that gives you kind of a, almost standard type language sequence that you can reference, right? Or anything that's kind of contained in a spec. All of these systems need to be compatible with that, which kind of lends to the modularity that I've talked about above. However, where the industry is right now, there are some gaps, and I like to kind of present this case study where I got a bit frustrated with a lighting system. So building A here has lighting as a separate standalone system. Both of the buildings were intended to be fully BACnet and have everything on a flat IT network on BACnet. But in this case with building A, the lighting was on a standalone proprietary system. It had a BACnet device at the top of the system, but that BACnet device wasn't actually able to route traffic from the underlying lighting system. So we ended up in a problem with this because we couldn't actually take the occupant sensors or occupancy sensors, the passive infrareds attached to the lighting system, and actually feed that data directly into the automation system. So we had to have some sensor redundancy to actually get the occupancy data from the spaces. So this became kind of tricky and kind of frustrating and cost, a fair bit of money to duplicate the sensing capability. In some cases, we even had to put in standalone sensors for research purposes here. Building B, it was fully integrated all on BACnet. And then in this case, we were able to pull in a lot more data. You can see kind of the sensor density essentially doubled, or the square meters per sensor or square feet per sensor was cut in half. And then there was just a lot more data that could be pulled in this case. So you could actually use one sensor for multiple applications. So the occupancy sensor would be used to manage the lighting. There was daylight sensors that could be used to dim the lights and figure out what to do with the blinds. But ultimately, this is kind of one of the basis pieces of doing artificial intelligence, is actually having all the data be accessible, right? And this gets to my 4 S's of semantic interoperability. And this first one is kind of a system level thing where ultimately, and it doesn't have to be BACnet. BACnet's an ASHRAE standard. This is a presentation for ASHRAE. I'd like to refer to BACnet, but it could be anything where it's in one place. It could be an SQL database that gateways things in. That counts as tools, but ultimately you have to have all of your data in one spot to be able to view and operate on the data. And this is still a big gap in industry right now, and you get a lot of disparate and disconnected systems, which is an ongoing problem. Now, once you get there and you have all your data in one place, ontology becomes a thing, syntactics. So how do you know what things are? And a lot of systems, they might have, for example, analog inputs or digital inputs, and the name of these in the software or firmware will be analog input 1 or AI 1. And from there, unless you have a separate document that's connected to something, you have no way of actually knowing that that AI 1, and this isn't artificial intelligence, this is an analog input 1, is actually a room temperature sensor. And this is where your dictionary comes in and your metadata comes in, where you have to actually be able to take the physical assets and then in the digital asset space have something that actually tells you contextually what it is. Because if you remember when I was talking about large language models, and this is where it starts to come together, the second L there is language. So you need to actually have some form of natural language that a natural language processing system like a large language model can interpret, right? So now you've done 2 S's. You have all of your data in one spot. You have it labeled. But how do you access this data? Where is it stored? And this is the next structural aspect. And this is a bit of a gap. Some ASHRAE standards get into this a little bit. I've seen some ISO standards start to hover around this, but this is still very much an emerging thing that I think philosophically some people think that this should fall on the vendor. Maybe. I mean, it depends how interoperable you want things to be. And there are some specifications out there, for example, in ASHRAE 231, which I'll reference, I think, on a slide coming up very quickly. But there are still limitations to that, because when you look at, for example, ASHRAE 231, you're just looking at control sequences specifically, not a large enterprise scale database that contains time series data, real-time data, as well as metadata that tells you what these things are. Where do you put all this? And that gets very bespoke very quickly. Then the last S, semantic. You need to know the context of things, and this is why I put this image here, plant. Right? Plant could be a plant that contains boilers. It could be a green wall. This is kind of the final frontier that I don't know if we'll ever get to, because this is a weakness of natural language itself. So ultimately, if you've done everything else, context probably isn't an issue, but it is one thing to be aware of, that you need to be able to understand what everything is to connect it rapidly to these artificial intelligence systems. So in terms of standards, you have high performance sequence of operations, which gives you I/O inputs and outputs that would go into certain algorithms. So this is already pretty handy, because now you have templates on that you can work with in terms of expectation, and that's information you could put into a knowledge base that could be understood by these artificial intelligence systems. Then you have standard 223P, semantic data model for analytics and automation applications in buildings. So this ultimately works in harmony with things like Brick and Project Haystack, which gets to that ontology dictionary point that I had in the last slide, where you have to be able to have metadata labels in natural language that have contextual information of the system. Then you start to get to packaging all of this together and uniting it with respect to control sequences with a control description language for buildings. And all of these, some people might have seen a slide that I know other people do where you have puzzle pieces going together that basically has these plus BACnet as kind of the future of how buildings are going to start to be able to interoperate. And this is a big step in being able to rapidly deploy artificial intelligence systems. So in terms of data sources, and this is important because when you bring in project data into the system, you're ultimately working with drawings or data from within drawings, and you need to put it into this metadata ontology platform. So I've tried to draw it out a little bit here. So people here that are familiar with computer science, you have the concept of a tuple, which is a key value pair. It's two things, tuple. When you get to these ontologies, most of them, as they are today, tend to be based off of semantic web technologies. And semantic web technologies are built on the concept of something called a triple, which in this case is three things, where you have a subject, which is the source, an object, which is the destination, and a predicate that links them together. And a very simple example of this is VAV is a subject, occupancy sensor is an object, and VAV has point occupancy sensor. And when you're building the semantic web graph database, think back to the hype cycle I showed with graph technologies, right? This starts to become very powerful as a way of encapsulating the mappings and the routings of different information in a building system that can then be understood by other building systems. It's human readable, it's machine readable, and it's a way that you can rapidly configure things, which is why I thought it was important to show this. Also, at one point, this was a few years ago now, I built a basic JavaScript interface where you could take point IDs, point names. It would read those in from a BACnet device, and then you could start to put brick tags on things. And this was very useful because this actually interacted directly with the BACnet tags property. So you could then embed this within BACnet data on a building automation controller. Do I think this is the best way to do it now? I don't know. I mean, it's a good way to be able to access the data and potentially access it from a third-party system that can read BACnet and route through the different protocols and gateways. But kind of this is supposed to be a bit of a tractable example where you can see DAT is discharge air temperature sensor, and you can see how all of these start to relate to things like the VAV, the hallway, and all of these have proper names and locations that would make this start to look like a bowl of spaghetti if I showed all of it. But you get the idea of kind of how you can assign metadata tags that can then be taken from key value pairs, these tuples, and turned into triples, and build out this kind of larger map of the system that's ingestible by artificial intelligence systems. So working my way up from kind of basic devices and stuff you could do on one device all the way up to things that you can do with kind of larger systems and this metadata. I want to start with sensor fusion and something basic like temperature sensor fusion. This is kind of on the edge of what I would consider artificial intelligence because it is machine learning. Well, it's not even really necessarily machine learning. It's kind of on the edge of machine learning. At the base of this is something, and don't worry about not knowing what this is, called a Kalman filter, where you basically have a model and you update the model based on errors and readings. It's technology that was associated with early space travel where you don't have a GPS system. And your only point of reference is the last thing that you did, right? So the idea behind this is that you can remotely read temperature below, and then you don't actually have to be as close to something to understand what the temperature is. So in this application, we're looking at operating rooms. I've referenced another ASHRAE standard here and some requirements of that. I'm not going to read them out loud. But ultimately, the concept is instead of using a wall-mounted temperature sensor and a thermostat, what if we used a ceiling-mounted temperature sensor coupled with an infrared temperature sensor to estimate the temperature of essentially the warm mass below, right? In this case, it would be a human being operated on, where the goal of, maintaining temperature control in operating space is ultimately for the success of the patient. not to make sure the wall is the right temperature. So the idea behind this is that you could monitor temperatures inside the air curtain without actually having to be inside the air curtain that goes over this operating table. So this was a case study that used what we call a composite temperature, which is a combination of the air temperature on the ceiling and the infrared temperature that comes out essentially in a cone from the ceiling mounted sensor. So there's some graphs, but it takes a while when I go to the graph analysis, and I'm already running a little bit behind here. But really what happened here, and you can see some of these ceiling mounted sensors all over the place, and they can kind of be pointed a bit more towards the operating table. You get less hunting because you're not using the discharge air temperature sensor as a reference. It's a tricky space, and cleaning is very important as well. Because sometimes when you're in an operating room, blood gets everywhere, and you got to hose the whole thing down. And you could still get blood on the ceiling, but you're less likely to get blood on the ceiling than other parts of the room. So you'll get better response with infrared temperature as well. You don't need the air to blow over it. You don't have to deal with the thermal mass of a thermostat or other things irradiating a thermostat like warm equipment. And then ultimately having a remote temperature reading with infrared temperature readings on the ceiling and a model to calibrate that automatically allowed for better compliance with ASHRAE standards in the particular case study. Now another sensor fusion example here. The goal here was to estimate occupancy without a camera, and this contains a kind of a deep learning model. An artificial neural net model inside a edge device, and I'll show a graph on the next slide that sort of shows why you need to do this at the edge. But the concept is, if you don't put a camera on something and you already have a bunch of ceiling mounted sensors, can you start to put this data together to estimate occupancy and validate it against camera-based systems, or someone literally going into the room and clicking a button and saying, okay, there's 5 people in here. So this used the composite temperature from the previous sensor fusion example I talked about, used relative humidity, luminosity, which is the like the lux level, passive infrared with a standard PIR sensor, and kind of more granular analog to digital readings than you would than just the 0 to 1 output from the sensor, as well as closed circuit microphones on device as something else to supplement it. Now, in terms of evaluating the validity of the model, mean absolute error was one of the metrics, but also a metric that we called persons within 2, which is the amount of time through all the samples that the error was less than 2, which ultimately we kind of sorted out from looking at different spaces and meeting room occupancies that this was an acceptable level, right? Because you could do 0 to 1 really easy because of the PIR sensor. People are actually in the room or not in the room. Like 99.9% of the time. But then once you get above 2, that's where it starts to get interesting. So in this case, kind of taking this thing and encapsulating it as a BACnet object, the reason this has to go on the device is because of the rate at which the analog to digital count from the passive infrared sensor varies. So you have to do something called downsampling in this case, which is you look at the passive infrared sensor reading, which comes in at sub-second intervals. We're talking like 20 times per second. And then that gets smoothed out a lot, and that's kind of the main input to this particular system to estimate the occupancy count over time. So you can see how erratic the passive infrared sensor reading is and how smooth the estimated occupant count in the room is over time. And this is with the downsampling as well. So ultimately, that's kind of the trick to it, is doing some waveform transformations and putting in an artificial neural net model on an edge device where you have sample rates that are much faster than you would get from pulling it out of a system, which is where this gets kind of interesting, and where you have machine learning really at work to do things on a packaged edge device, applying model. So yeah, it kind of preserves privacy. It's close enough for most applications. Think in terms of DCV and the accuracy levels on a CO2 sensor, which anecdotally I have found are all over the place, which is why I'm kind of excited about this type of an idea, because I've had so many issues with trying to read CO2 sensors over time. But yeah, we also found Typically meetings are or under 6 people. 86% of meetings were 6 people or less. You can get pretty good person within 2 metrics most of the time through the training data that we use to validate the model. And this is the type of thing that can kind of be rapidly deployed in the field, and also is something that can kind of, you know, supplement thermostats and things like that. So it's got a lot of sensing in it that you need to do anyway, and then you can also do additional things by embedding machine learning in the system. So now this is the part where I get to generative AI, which is where all the hype is right now. I like to give the disclaimer for generative AI, which, full disclosure, generative AI helped me write this, except for the quote at the bottom. That was something that someone told me. But I put Plinko here because there is a stochastic element to this. There is some random stuff that will happen when you're interfacing with a large language model, and you won't always get the same response all the time, right? But you should get something that's close and starts to meet your application if the system is designed well. So accuracy is, of course, based on the data that it's trained on, which is the importance of ground truth data, which I really hit home in the conclusion of this presentation. Context, it's a machine learning model, ultimately at the core. So it doesn't know any context on the data other than what you give it. So it's going to rely on, again, the data that it's given. The bias is going to emulate the data that it's given and trained upon. The results have to be interpreted in a way, and the AI system might not interpret it the way you would expect. Probably there needs to be a layer of human interpretation at the end, depending on what you're doing. And responsibility, this one's tricky, and people have argued about this. In my opinion, the user is responsible for the output of the AI system, or whoever, vends stuff. This becomes very legal very quickly, so this is why I don't like to talk about that too much. But yeah, someone at ASHRAE one time was kind of talking about their experiences with large language models, and they said it's almost like talking to real people. Sometimes you'll get good answers. A lot of times you'll get usable answers. Sometimes you'll get crazy answers that don't make any sense, like talking to real people. So this is something I did in late 2024 that kind of ties some things together. So you could start to get tabular data. Most building automation systems will be able to give you some sort of tabular data output. So from there, this is where, I don't know if people are familiar with the term vibe coding today, but ultimately it's kind of working with a Copilot coding tool and generating code. So I did that in 2024 to basically build a very simple program that would take the data in this table. It understands the schema of what's going in, and then the schema of what comes out. And if you remember when I was talking about these semantic web graph models, you can then take this table, do some vibe coding, and rapidly generate and this is a visualization of it, a semantic web graph model of the system, where you can start to link the real assets with addresses. Well, I guess this is the digital representation of the real asset, but if you send a command there, it'll do stuff. All the way up to different ways that metadata is applied. And all of these things that come from something like BRIC will have a definition of what it is, and this is something that a large language model can better understand. Looking at starting to leverage templates. So this is something that, I feel I've been doing a lot of work on lately, and I get very excited about, is this concept of automating building automation system programming. And I think there's been some systems that have started to do this kind of on simpler systems. I've been trying to explore taking VAV airside systems and leaning heavily on Guideline 36 templates. If you have a semantic data model and metadata associated with all these different assets or digital representation of assets in a template, can you talk to a chatbot that's connected to an agentic framework and start to morph those templates into the thing that you actually want for the thing you're trying to program? And this is where a lot of the copy paste errors can start to be eliminated, and you can start to do if people are familiar with the term CRUD, this is a create, update, delete, and I forget what R is, read. But you can start to do what I like to call exotic CRUD, which is different updates and deletions of the system, and then being able to do that with a large language model to understand the actual action you want to do on a database system that's ultimately all that these computer systems are that do building automation system programming, and then to do that rapidly. This is something that I think is going to change things very quickly. The core of this is large language models, templates, semantic data modeling, and kind of somewhat canned algorithms. So all this kind of comes together with the standards I talked about and kind of the AI readiness things in terms of semantic metadata. And on top of this, because you're using a template that contains semantic metadata already embedded within the system, it basically would port your semantic metadata. So that kind of gets interesting when you start to think, okay, how do you put a third-party system on top of this? Well, you already have definitions for everything. It's linked to the assets, and the assets are able to be controlled through APIs, which is kind of the way things are going, where you start to have everything on that, one layer that everything can be interacted with. I actually did this next thing first, and this is connecting a large language model to a building automation system. But I realized that you really need a heavily curated building automation system in order to actually do this, which was a big limitation, which prompted everything else. So ultimately, I kind of asked some questions to a chatbot that was connected to a building automation system and API that had a bunch of semantic metadata in it already. So asking it about the room temperature, you can see the JSON response, controller IDs, site names, object names, and then where it is. And then you kind of go through this. And this was an interesting process where unprompted, we got some analysis from a large language model. This was in 2023. So we asked it for the current temperature. It gave the current temperature. We asked it for the temperature an hour ago. At this time, it was a RAG system, not an agent. Well, sort of. It was a very light agent system. One agent, which anyway, I don't want to debate that. But it was able to access an API that could go into a BACnet trend log and then pull data historically from a buffer. This starts to get particularly interesting where you ask for the record over the last 7 days. And it starts to think something's wrong here. And I didn't mention this before I introduced this problem, but we were running this with a virtualized controller. So the virtualized controller didn't have real inputs connected to it, so it had a static reading the whole time. And then from this, it was able to notice that the reading was static over the last 7 days, say that it was in a fault condition. And then this was one of the big features of GPT-4 that got very exciting, is being able to output PDFs with a report and giving you things for administration, like go look at the sensor, implement a more rigorous monitoring and maintenance program, maybe put redundant sensors in because you have asked 3 times what the temperature is in this room, right? So it starts to be a bit insightful, and things have even come a long way since then. Kind of a real quick rip through predictive control. So this is kind of like your basic thing from Wikipedia of what predictive control is. You have measured inputs, measured outputs. You have a reference trajectory. So you're trying to most efficiently, based on a cost function, operate the outputs of a system with predicted inputs and predicted outputs. So this gets very complicated. Even a VAV system ends up having about 50 different parameters that are important and need to be measured, because you have to measure them at multiple time steps in the future. The concept I was exploring here was, what if we just made this into a classification tree with kind of basic conditions, and if those conditions are met, my apologies on the significant digits, you will know whether to continue operating the system as usual with a binary output of 1, or override and do something different because you're going to be wasteful based on the cost function. There's a lot of background to this. I've written a couple papers on this. I'm going very high level here. But ultimately, this was a balance between thermal comfort inferred by room temperature set point and room temperature, as well as the predicted energy used through a virtual sensor, which I know is not really truly comfort, but at the time it was what we had access to. So this was a pretty highly instrumented space with indoor air temperature sensor, relative humidity, CO2 concentration, occupancy. We had plug loads. We were monitoring the lighting state. We were monitoring the lighting power, as well as the illuminance at 3 different depths. return air temperature, outdoor air temperature, window state, open or closed, blind position. We had a full analog on that, as well as BTU meters on the radiant heating system, as well as the VAV coils and kind of your typical VAV sensors. So ultimately, anytime you're starting to build out a machine learning algorithm in a building, you're going to need to train it. If it's a black box or a gray box model. So you need a couple weeks of training data. You can then program it with the updated parameters. And in this study, I did full predictive control, and then I did what I call rule extraction, which is basically replacing the full predictive control with the 50 different inputs and parameters with a classification tree instead, very simple, like what was there before. On the last slide, because you can put in Boolean rules that loop inside a device much easier than you can large matrices, especially in resource constrained legacy devices. So yeah, ultimately this is kind of the tree of the process with respect to set point, temperature sensor, season, as well as 3 time steps of energy forecast. Again, I won't go too deep into this, but this sort of shows that there was a meta heuristic that was on top of the heuristics of actually meeting the cost function. Now, what was interesting here is I wanted to make sure that the classification tree for how to override or not override a zone operation mode wasn't too complicated, but also was reasonably accurate. So a couple of different cases here where I went through what's called a random forest, which kind of iterates a bunch of different things. And there's a stochastic element that'll give you a different tree every time and different thresholds every time. But you can see there's kind of an inflection in complexity, or there's a jump in accuracy improvement. And those are different ways that you can start to select the proper tree, which if we go back a couple of slides, ended up being this for, I believe that was the heating. No, that was the cooling season. Yeah, and these are north-facing offices. That's why there's no illuminance sensor there. But ultimately, that gets very complicated. I'm sure some people were very confused about that on this call. And this is why, going back to what I said about scalability with AI, you need systems that are interpretable by operators or management or whoever's going to be responsible for administrating this system, right? So being able to put the real override limits, which in this case I've used halfway between the occupied and unoccupied set points prescribed by ASHRAE Guideline 36, and then just a basic slider that manages that cost function between thermal comfort and energy. This is ultimately the type of interface I think is required to be able to do more complicated algorithms, even at the zone level, in a way that can be administered and have a level of trust, which gets to this AI constraints thing, where constraints are very important, and having some sort of input and feedback to the system as well. So yeah, all these different predictive control modes, whether it was full predictive control or this simplified rule extraction, ended up being really between 20 and 42% energy savings. And this number probably would scale down because this particular building actually had a 24/7 schedule when I was experimenting on it. And there were a few other inefficiencies in the building. I think, even with a 24/7 schedule, you could probably cut this in half. And this is probably like, 10 to 20%, which is very real. But you get to a point where the baseline in doing these studies becomes very important. And this is where I point to Guideline 36 again, is providing you something that you can use as a baseline and kind of everyone's agreed upon as an operating mode for controls. But when you don't have that, which I did this before Guideline 36 was a thing, you'll get numbers that are a little bit all over the place, right? But you could still scale the results out there. I know a recent paper by some pretty notable people in the field of predictive control put it between 15 and 25% of potential energy savings for implementing predictive control. But ultimately, when you're doing that, you're starting to solve some other problems as well, which is where you're not just doing predictive control to save energy from a regular baseline from forecasting things. You're stopping other issues that would have occurred in overrides that you're doing. So yeah, to conclude, this first point, be careful when you're doing it, but it's true, right? You have to think about all the different aspects of what you're connecting to, what you're overriding. Are you going to cause new problems by implementing a machine learning or artificial intelligence program or system into your existing system? semantic interoperability whenever you're dealing with language models is super important, and is a prerequisite, which is why I talk about it for at least 10 minutes in this presentation. I think applications need to be constrained to simple problems first and then scale up, which is why I always try to start with zones first, because that's kind of, the first thing that you're really controlling in most building automation systems at the commercial scale. And then I think as we see more structured metadata, you're going to see more adoption of these systems. And that kind of ties to my S's of semantic interoperability. And of course, ground truth is gold. When you're building these data-driven models, which everything that's an AI model or machine learning model is inherently data-driven, you need to actually have the data to fit the model, or at least data to tune a model, which is why we need to actually get that data and be able to have access to it, which there are various initiatives out there that do provide data that can be used. So yeah, I think we have a few minutes for questions. Thank you so much for sitting through this, and I'm happy to answer anything anyone's got relevant to the topic, or maybe not.
Cheers. Thank you very much, Jason. Really interesting. I'd like to open the floor for any questions. So please put your mic on or type it in the chat, and I'll be more than happy to read it out. I think as people type or put their hands up, I've got a couple of queries. I'm quite interested on the. Oh, there's a hand up. Go on. Yep.
Oh, you're on mute if you're talking. Sorry.
Yeah, we had the. Can you hear me right now?
Yeah.
Yeah, I'm Serhat from Air Products, Texas. Yeah, I had a question about occupancy sensor fusion. It is about sensor fusion, right? Combining different kinds of sensors. And in the second slide, I remember you mentioned just noisy PIR sensor. Is this a second part? I mean, or it is combined sensors?
Yeah. So the PIR is just the direct signal from the PIR sensor, right? Now, often what will happen when you get the sensor reading from that sensor that goes into kind of a supervisory control system or on-device control, that will have a filter on it that really smooths the signal out.
Okay.
Yeah, there's already inherently some filtering and downsampling going on in these systems. They're quite noisy sensors when you look at the analog to digital values that come out of them. Yeah. But yeah.
I was not sure. Yeah, it is just predicting based on noisy PIR signal, the occupancy number.
No, it uses all five, but
okay.
It's heavily weighted towards the noisy PIR sensor. Yeah, that's why I like to show that one. Yeah, because the other stuff, well, the mic signal moves a bit, but the mic signal tends to be more of a binary input to that particular sensor fusion technique. The PIR is where there's a lot of scale and waveform transformation going on.
Anderson, thank you.
Oh, it's me.
All right.
Hey, Jason, it's very good.
Wait a second. You have.
Oh.
Yeah. Hi, Jason. Very good presentation. I have the question that we have, because given that data side, we have huge data like for time series, for building wise or for just HVAC, if we have like a 10,000 HVAC, what kind of the best database, in that. Now, I think in your document, you show the SQL. Is that possible? Like you think that use a graph database, like a land graph, to calculate land chain to design a multi-agent, AI system? What's your opinion for database?
Yeah. So I talked a lot about graph database, and I did mention SQL as a way to store schema data. It could be time series data. You could put that in SQL as well, right? I think it needs to be both. Like you need the graph database as a way to map to the actual location of the time series data, and that needs to be a clear time series reference. And some of these metadata ontologies, they do have classes or predicates for time series references. And I think actually 223 has something that does this, where you would basically take that and you would point to whatever a URL is or a URI for, well, no, URL in this case, for that time series data location, right? And that could be mapped to an SQL database or something like that. Really, any way to get to it. So you need to put them together, and anything in just time series data, I think, needs to be referencing the graph database or something like that to get to the time series data. I think it'd be really inefficient to try and put time series data in a graph database. And as far as I know, most systems that deal with this keep them separate, but use the graph as a reference to the time series data. Does that answer the question?
Yeah, pretty much. Thanks.
Awesome. Thank you.
Perfect. I think we've got a hand up from Kelvin.
Yes,
Oh.
it's Kelvin.
Yeah, no, that was Kelvin that just asked the last question. I do see one in the chat.
Right. Okay. Sorry. Right.
Yeah.
Wait, was it Kelvin? Did you ask the last question? Because for some reason it was coming out from someone else for me. Maybe it's just my computer.
Yeah, correct. Actually, Kelvin and we are sitting in the same room, so I think. Kelvin
Okay, that explains it. That explains it. Okay, perfect. Yeah, there's a question on the chat going slightly deeper. There are feedback control systems deployed in temperature control and EXV control. How do you see AI being employed for this? Does reinforcement learning sound like the right direction for it? It's on the chat.
Yeah, this is interesting. So I've experimented with reinforcement learning a bit in the past. So when you're simulating it, it requires a lot of data. I think a lot of algorithms out there do use a really simplified and modified form of reinforcement learning. And I think there is some promise to this, right? Like when you're doing reinforcement learning, you're starting to get to this model-free environment, which is, in the field, less data hungry, but you have to have a good spot to start, right? I think it's a good path, but I think that there is a lot of uncertainty when you are using reinforcement learning systems, and there has to be kind of some understanding from the occupants that operate the system that there will be some weird blips, right? Yeah.
Perfect.
Okay, it's Kelvin again. I have the question that because large language model for us, it's very big, and take lots of memory. And normally we have to put it in the cloud, right? So, but for our edge AI, like HVAC, do you think we should use a small language model? And if so, do you know, is any small language model in HVAC industry already available and open sourced?
Yeah, this one's tricky. Now, HVAC industry specific, I'm not aware of anything. I played with some large language models that you could fit into, the RAM on like a 2015 era laptop. I played with GPT for all at one point, and that's a heavily quantized version of, I forget which model. It might have been Llama, but don't quote me on that. Would I put a large language model directly in an HVAC system on-prem? Honestly, I don't know. I think it depends on the scale and the application and kind of how much, you are looking to actually improve operations and energy savings, right? And when I say operations, I mean like maintenance, frequencies, thermal comfort. There is some stuff that you can host on maybe like a $10,000 PC with a video card in it that's not too bad, but nothing really specific for this industry. I mean, kind of going back to what I did with predictive control, my thought is if you really need to on-prem this, you probably need to start looking at metaheuristics on top of things. But you could put a large language model in, but your performance really starts to degrade quickly for a lot of applications when you on-prem it compared to cloud. At least in my experience.
Okay, thanks.
Fantastic. I don't think there's any more questions. If so, now's the time. If not, thank you very much, Jason, and all of you for attending and joining this session. And I wish most of you the rest of good of day. It's that's it. We're done for the day, so looking forward to going to bed. So the recording will be uploaded on the Ashray UK